Imagine a world where you could step into any video and interact with it like a living, breathing environment. What if AI could not just generate stunning visuals, but create persistent worlds that remember your actions and respond intelligently over time? Today we explore groundbreaking research that transforms video generation from passive dreaming into interactive world simulation. Let's start by understanding what makes this problem so fascinating and difficult. Building on that vision, the researchers identified 4 critical barriers. Most video generation models produce beautiful but disconnected clips that lack the persistent logic needed for true interaction. Meanwhile, the few systems that do achieve interactivity remain locked behind proprietary walls. So what would a true world model actually need to achieve? The authors frame this as learning transition dynamics through conditional generation, where the system must predict future frames given past context and user actions. Now let's dive into their elegant 3-pillar approach to solving these challenges. LingBot-World tackles the problem through 3 interconnected innovations. They built a sophisticated data engine that understands video at multiple semantic levels, then designed a progressive training pipeline that gradually introduces interactivity and real-time constraints. The data foundation is crucial here. Rather than relying solely on passive web video, they created a hybrid training corpus combining real exploration videos, game recordings with synchronized controls, and Unreal Engine synthetic data. This synthetic component is particularly clever, generating collision-free trajectories with ground truth camera parameters that would be impossible to obtain from real footage. What makes their data engine special is the hierarchical captioning system. Instead of simple descriptions, they generate multiple complementary captions that disentangle different aspects of the video, from high-level narrative to precise temporal events. Let's examine how they progressively build interactivity through their 3-stage training process. Stage 1 establishes the visual foundation by starting with a proven video generation model. This gives them a strong canvas of texture quality and basic spatiotemporal understanding before adding the complexity of interactive control. Stage 2 introduces the core world modeling capabilities. They implement a mixture of experts approach with 28 billion parameters, where high-noise experts handle global structure and low-noise experts manage fine details. The action conditioning is particularly elegant, using plucker embeddings for camera rotations and multi-hot vectors for keyboard controls, injected through adaptive layer normalization. The progressive curriculum is key to achieving long-horizon coherence. They gradually extend training clips while using parameter-efficient fine-tuning to avoid catastrophic forgetting of the visual quality they worked so hard to establish. Stage 3 solves the real-time interaction challenge through causal adaptation and distillation. They replace the expensive bidirectional diffusion with block causal attention that maintains local coherence while enabling streaming generation. The discriminator helps maintain quality during the transition from teacher to student models. The distillation process is sophisticated, using distribution matching to transfer knowledge from the bidirectional teacher, while adding adversarial training to maintain perceptual quality during the compression to real-time inference. Now let's explore what this elaborate training process actually achieves in practice. The results showcase remarkable emergent behaviors that go beyond what was explicitly programmed. Landmarks remain consistent even after being out of view for up to 60 seconds. And the system can plausibly evolve unobserved states, like a moving car continuing off-screen. When evaluated against baselines like UM 1.5 and HY World 1.5 on the VBench benchmark, LingBot-World demonstrates superior dynamic degree and temporal consistency. The quantitative improvements reflect the qualitative leap in interactive capability. The applications showcase the system's versatility. They can inject weather changes or objects while maintaining physical coherence, train navigation agents within generated worlds, and even reconstruct 3D geometry from the generated videos as evidence of spatial consistency. Every breakthrough comes with honest limitations that point toward exciting future directions. The authors are refreshingly honest about current limitations. The memory system relies on attention rather than explicit storage. Compute costs remain high, and the action space is currently limited to navigation rather than complex object manipulation. These limitations outline a compelling research roadmap. Future work could integrate explicit memory architectures, expand beyond navigation to fine-grained manipulation, and tackle the fascinating challenge of multi-agent world simulation. Let's step back and consider the broader implications of this work for AI research and applications. This work represents more than a technical achievement. By open-sourcing interactive world simulation capabilities, the authors are democratizing tools that were previously locked behind corporate walls and accelerating research across multiple AI disciplines. LingBot-World transforms the dream of interactive AI worlds from science fiction into accessible reality, proving that sophisticated world simulation can emerge from the marriage of video generation, action conditioning, and progressive training curricula. Visit emergentmind.com to explore more cutting-edge research that's reshaping the boundaries of artificial intelligence.